Thank you, Tatiana, and thanks for inviting me. So when I was in high school, I took Russian language class, which was newly offered in the United States. And I've always wanted to come to Russia. So I'm here. It's amazing. Great place. And St. Petersburg in particular seems like a nice place. So anyway, what am I going to talk about? So what do I do? So the topic of the talk is moduli spaces of graphs. So I want to study moduli spaces of graphs. I also study moduli spaces of other things like surfaces and cat-zero complexes and things like that. But today we're going to keep things very simple and just talk about graphs. So I should tell you what I mean by graphs. My graphs are going to be finite graphs. And they're going to be CW complexes, cell complexes, which means they've got vertices and edges, but they're also allowed to have loops or multiple edges. Okay, so they're not simplicial graphs, they're not simplicial complexes, they're CW complexes, cell complexes, glued out of vertices and edges. Okay, right. So in addition, my graphs, well, for part of the talk, my graphs will have lengths on the edges. So I'm going to put positive real numbers on the edges. So the lengths are in positive reals. So these are, I can also think of these graphs as metric spaces. Right, so such graphs show up all over math and science. I'm going to give a couple of relevant examples. So these model things. So for instance, people who study biology like to model phylogenetic trees. So that's also called a gene tree. The idea is you have some species, maybe an amoeba up at the top. Let's not make it very complicated. Maybe a person, a cat, and a dog. And you have some data, and you want to know whether the cat and the dog are more closely related to each other to a person. So you want to know whether the gene tree looks like, whether the species tree looks like this, or like this. Cat over here. The amoeba is always up at the top. Okay, so if you have such a tree, it would obviously, if you're actually a biologist, be much more complicated and you'd be studying more things. But the important aspects of this tree, you might assign a length to this edge. The length of the edge would have some meaning, such as the time between speciation, or the number of differences in the gene for some basic animal process, etc. Okay, so these graphs are going to have lengths on the internal edges. Actually, the lengths on the leaves don't matter, so the leaves are labeled. The lengths are irrelevant. So this was ancient history, and this is now. But what we really care about is how is this number here, the length this time. So that's one example of a kind of a tree that you might like to study. The second example I'm going to, it's going to motivate me a lot in this, is the example of Fineman diagrams. So in physics, if you have some scattering process, you have particles going in, particles coming out, and something happens in between. But you don't exactly know what. And you want to assign some amplitude. So this is a scattering process. You don't really know what happens inside. You know what comes in and comes out. So to this thing, you want to assign an amplitude A. So this is a function. It's going to depend on the momenta of the incoming and outgoing particles. It's a complex number. On the external momenta. And you can't compute it. It's impossible to compute. So what you do is you make approximations by writing down a perturbative series a sum of a bunch of terms, and each term corresponds to some possible thing that could have happened in between. Okay, so you break this complex number, which you can't define, into a bunch of other complex numbers which you can't define. And so each term is some ill-defined integral that kind of is exemplified, that corresponds to a certain graph with leaves on the edges. And you can naturally group the terms by what the physicists call the loop number, which is just the fundamental group of the graph. And then this integral that they can't calculate, they write as each term is an integral over a space of metric. Has a lot. Well, there's lots of different ways to describe the integrals that give you the terms, but one way is as an integral over the space of metric graphs with that shape.
Sorry, what did you write just above?
Okay, the terms, so I've got this amplitude I'm trying to compute. It's a complex number. It's written as an integral I can't compute, so instead I break it into terms. I collect the terms. The terms collect into terms corresponding to a graph. And the terms are grouped by the loop number.
Yeah.
So I put all of the numbers with one loop in the same picture. And what I'm doing is each term is the integral over a space of metric graphs with a given shape, with a given, loop number. And in fact, the entire thing can be thought of for this, What you're doing is integrating a certain distribution over this space, it turns out. Okay, so, right. I don't really, that's another reason. So what I'm trying to do is give you reasons we might want to understand what these moduli spaces of graphs look like. So this is supposed to be motivation, this part of the talk. I'm going to pass to motivation strictly from mathematics. That comes from group theory, where I can say things with a little bit more authority than I can about phylogenetic trees and Feynman integrals. So what about group theory? The fundamental group of a finite graph, G, is a free group. Okay, so that's a basic fact. So if you choose an identification of the fundamental group of G, I1 of G of the free group, that's an isomorphism. That's called a marking. Okay, so if I have a graph with a marking, and if I have a homotopy equivalence from G to itself, that means it gives me an isomorphism on the fundamental group. Then if I have an identification of the fundamental group with Fn, that also gives me an automorphism of the free group. So what I'm saying is if I have a homotopy equivalence of G, I get an automorphism of the free group. That's this picture over here. But I was pretty sloppy when I said what I was doing here. When you talk about fundamental group, you talk about loops at a base point. I didn't give you a base point. When you talk about homotopy equivalences, well, if I have a homotopy equivalence, it doesn't necessarily send a base point to a base point. So in fact, this map isn't really well defined as an automorphism of the free group. It turns out it's only defined as an outer automorphism. And if I have homotopy equivalences, then I get the same outer automorphism. So I actually have a map like this. And turns out it's not very hard to see that that's an isomorphism. This group is called the group of outer automorphisms of the free group. Okay, so there we've got graphs and we've got a group, and we've got homotopy equivalences of graphs and we've got automorphisms.
So you consider the binary automorphism, you mean the automorphism which you get by conjugation?
Right.
And so this factor is a factor, yeah? Yeah.
This is a quotient. Yeah. So the point is, if I want to, if I want to think of this as a map on fundamental groups, I have to choose a map from the base point I had over here to its image over here. And I can choose a lot of different paths, and if I choose a different path, I'll conjugate this automorphism. Okay, so a homotopy equivalent gives me that. So yeah. So now I want to look at the set of marked graphs. I claim that this group of outer automorphisms acts on the set of marked graphs. So how does that work? If I've got a certain marked graph, so that means I've got an isomorphism between the free group and the fundamental group of my graph. That's an element of my set. And now if I have an automorphism of the free group, I get a new isomorphism from Fn to the fundamental group of my graph. Okay, so out of Fn acts on this set of marked graphs. If you remember, my graphs had lengths on the edges. So I can make this set of marked graphs into a metric space by saying two points are close if the lengths on the edges are close. So it looks like the same graph or very close to the same graph, but this set becomes a space if lengths of edges are close. Space. Make lengths of edges close. Okay. This space, I'm being very sloppy, I'm sorry, but I can, yeah.
This is how you make this space of graphs.
This,
to be a metric space.
Yeah.
What about markings?
Well, okay, so if I have a graph, it's got comes with a marking. Yeah. I can think of that as a homotopy equivalence from some fixed graph if I like. And then I just say if I vary the edges a little bit, make the center one a little bit shorter, maybe, then that's close by. But it has to be the same marking. Okay.
So here all graphs that we compare are homotopy equivalent, right?
They're all homotopy equivalent.
We are reading one homotopy equivalent.
Yeah, they're all just they all have free group Fn. Okay. So group theory. So what do we have? We have fundamental graphs with finite graphs. They've got a free fundamental group, and we have the set of marked graphs on which the group of outer automorphisms of the free group acts. And we can make it into a space. This space has a name. It's called outer space. I sometimes get very interesting audiences when I advertise that I'm going to talk about outer space. But yeah. Okay. So what? We've got a space, and what makes it an interesting space is a theorem proved by Mark Culler and myself in 1986 that the space, the outer space, is contractible. Out of Fn acts, as we know, but the it has finite stabilizers. And the quotient, so it acts, and how does it act? It just changes the marking. It doesn't do anything to the graph. Right? It just changes that marking to that marking. So the quotient is the moduli space of marked graphs, of unmarked. Graphs. So that's what I was trying to say I was interested in over here. I don't have any markings of my graphs over here. I don't have any markings of my graphs over here. But here I've got markings, but I've got a contractible space with a group action, and the quotient is the space I'm interested in over there. You may object that that graph doesn't have any fundamental group, and this graph has lots of leaves, and I haven't really said anything about leaves, but actually I would like to assume in this discussion up here that my graphs in G have valence at least 3. Okay, so I don't have any leaves in this picture.
Excuse me, how should we think about this outer space? It's kind of universal covering of the space of all matter graphs.
It's an orbifold covering, right? The action isn't free. So if the action was free, then it would be a covering space. It would be, in fact, the universal cover. But since it's got finite stabilizers, it's not a free action, and the quotient isn't. So I could, and I often do, give entire colloquiums where I describe this space and draw lots of pictures. But I want to say something more today, so I hope, so I'm being a little bit sloppy, okay? Okay, so what if I want to think about leaves, and what if I actually am interested in the automorphism group instead of the outer automorphism group? Well, then I have to have graphs with base points. My homotopy equivalences have to preserve the base point. So if I want to a space with odd of Fn acting, need graphs with base points. So G and a base point. And then the same picture up here, instead of, I'll look at homotopy equivalences of my graph, but they have to preserve the base point. And then I'm going to map to automorphisms instead of outer automorphisms. And again, homotopic maps give me the same outer automorphism, and this will be an isomorphism. So if up here I'm looking at graphs with no base point, down here I want to pick a base point somewhere. And one way to do that is stick a little edge, a leaf, a univalent vertex onto my graph and call that the base point. That's a convenient way to do it. I forgot to say why this is interesting. So I've got a space, I've got this group action, it's contractible, the group acts with finite stabilizers, so therefore there's basic theory that goes back to Hurewicz that says invariance of the quotient space, which maybe I'll give a name, the moduli space of graphs with fundamental group Fn of MGN are actually invariants of the group. Of out of Fn. In particular, what Hurewicz says is that if I take the homology of this space with trivial rational coefficients, that's the same as the group homology of out of Fn with trivial rational coefficients. But the message is, if you want to understand this group, you'd like to understand the space. For instance, the topology of this space will tell you something about the group. And actually it works both ways, since the homology of the space is the same as this algebraic invariant, the homology of a group. If you want to understand something about the homology of the space, you might use group theoretic methods to study the homology of the group. So that's going to come in useful eventually, because we are interested in the structure of the space, and knowing something about the group will give us more information.
I have not understood the picture of the outer space. Is it finite dimensional or infinite dimensional?
It is finite dimensional because of my box up there. So if you take graphs of rank with fundamental group Fn, and you insist that all of the vertices be at least trivalent, there's only a finite number. For instance, for n equals 2, the only graphs you can draw are that one, and that one. So there's only a finite number of graphs and I'm only adding lengths. Sorry?
Is that a disjoint union or no?
I was trying to avoid giving the colloquium talk where I only talk about what outer space looks like. No, it's not a disjoint union. So if I shrink this edge to a point, I get to this edge. So there's a line in my space from this graph to that, from this graph to that graph. Yeah.
Maybe just to visualize, what is the dimension?
Well, the way I've described it, so I've got two real numbers for this graph, so that's a two-dimensional space, two positive real numbers. Yeah. Here I've got three positive real numbers, so that's a three-dimensional space. So this is on the bound, so that's like an orthant, and this is in the one of the boundary pieces of that orthant. And the third picture? That one, that's also got three edges, so it corresponds to a three-dimensional orthant. I can have lengths, three lengths, and if I shrink the middle edge, I get that guy. So it's common to normalize. Okay, I'm going to draw pictures. I'm sorry. Yeah.
There must be a formula for the dimension.
Sorry?
For MGN, there is a formula. What is the dimension?
Yes. It's an exercise in Euler Characteristic. Let me do n equals 2. Let me do the picture of outer space for n equals 2. Because I've already drawn what kind of graphs you can have. There's just 3. So you often normalize. So the sum of the lengths is equal to 1. Just because it makes it easier to draw the pictures. Okay? So here we've got two lengths, A and B. So here's A and here's B, and A plus B equals 1 is this line. So if I have a marking, then all of these graphs along this line have the same marking, but the length of A and B is different. The one in the middle, the two graphs have the two edges have the same length, etc. On this one, the sum of the lengths is 3. And so I've got 3 guys. The sum of the lengths is 1. So I'm going to get, this is A, B, and C. I'm going to get A plus B plus C equals 1 is a triangle. And if I collapse C to 0, so that corresponds to a triangle. If I collapse C to 0, I'm going to get that edge which is glued at the edge of the triangle.
Yeah, but should it collapse both? Because you have a symmetry.
I'm not doing the moduli space, I'm doing the outer space. Okay. So yes, good point though. I've chosen an isomorphism, Fn, F2, to the fundamental group of that graph, right? That's my marking. If I switch A and C, that's a different isomorphism. So it's actually a different point in the simplex. But that's a very good point. That's where the marking comes in. When I go to the quotient, you're right, I'm going to, this simplex is going to get cut into 6 pieces, or divided into 6. And then this other guy goes like this. He's also joined along there. Now the subtle point is that, so if this is a, so if my marking sends A around like this and B around like this, and I collapse the middle edge, then A goes around like this, and B goes around like this. Now if I flip these guys and open them up again, I get a new graph that looks just like the old one, but A goes around like this and B goes around like this. So I've got two identical looking simplices. The difference between the simplices is the fact that the markings are different. And in fact, I can keep going. And well, the convenient way to draw the whole picture is to put it in this nice picture, which you've probably seen somewhere in your life before. Okay, so these are all, and then I have these, sorry, I have these fins kind of coming out on all of, corresponding to the barbell graphs coming out along there. Okay, so there's a reason that this picture looks like the tessellation of hyperbolic plane, which is that for n equals 2 out of F2 is isomorphic to GL2Z. So it's the same group and it's the same picture. The difference here is that there's this bifurcation that, I mean, that's the flat part, but there's all these barbell graphs coming out. I mean, so there's these two guys and there's a barbell graph there too. So in general, outer space is not a manifold, unlike Teichmüller space, say. Okay. Okay. Oh, yeah. I was afraid of this, yeah. But I'm glad you're interested. I mean, right. So where was I? We have this outer space for graphs with no leaves. If I put one leaf on my graph, I get a related space with a slightly different group acting on it, namely the group of automorphisms. But my graphs over there all had a whole bunch of leaves, so if I put a bunch of leaves on my graph, I also get a space. Yeah, and I'm running out of space. If G has K leaves, I also get a space, the group. Well, it looks kind of like those groups. It's homotopy equivalences of something with K leaves. But it has to fix all the leaves, fix all these points. Fix all, think of this as a bunch of base points, they're all fixed. And that's definition A and K. It's another group. And there's a space. O and K, defined just like that one. And quotient M, G, and K. So this would be the moduli space of graphs with fundamental group Fn and K-labeled leaves. So that's the kind of thing we're interested in when we're studying Fineman diagrams, for instance. Okay, that was the motivation. Right. Right. So the moral of the story is we want to understand these spaces of graphs. And we have a nice tool for very many reasons, coming from various areas of math and science, of which I've only named 2, but there are lots. And we have this good tool for studying these spaces, namely studying these groups A and S. Okay. And then at this point, I'm supposed to point out that this picture of this space and this group action should be actually very familiar to you if you study, for instance, arithmetic groups. You study the action of, say, GLNZ or SLNZ on a symmetric space. Well, what is a symmetric space? It's a moduli space of marked flat tori, is how I think of it. Instead of graphs, you're talking about tori. You need a metric on the torus, and so you put a flat metric on it. If you're studying mapping class groups of surfaces, Riemann surfaces, then you use the Teichmüller space, which is the space of marked surfaces with either Riemann surfaces or hyperbolic surfaces, depending on who you studied with, who you wrote your PhD with. Okay, so the picture for out of Fn is really part of a long tradition of symmetric spaces and discrete group actions on symmetric spaces. Okay. Yeah, so what do we know? So MGNS, and did I call it K, is a moduli space of graphs with fundamental group Fn and K leaves. And we'll leave out bivalent vertices. Just to make sure the dimension is finite. Okay, so if n equals 0, then what are we talking about? We're talking about the space of trees. And we know everything you could possibly want to know about this space. So let me do trees with 3 leaves. No, that's too easy. How about 4 leaves? There's basically three of them. One's here, 3, 1, 2. That's all there are. And we only have one parameter, namely this length. Well, I forgot the one where that parameter has length 0. So what does this space look like? Well, there's that guy in the center, and there's 3 rays going out from this space, one for each of these trees. And if you normalize like I did to make all the lengths 1, well, there's only 3 points. So the space MG04 is S0 wedge S0. It's 3 points is what it is. And in general, MG0S is homotopy equivalent to a wedge of spheres of dimension S minus 4. So it's only got, so we know all about its topology. It can also be given a cat0 metric, which is useful if you're interested in studying phylogenetic trees, because you might like, for instance, to average trees. If you have some computer run, you got some species, you run your computer a whole bunch of times and you get different trees every time you run your computer. You want a consensus tree, so you want to average the trees. You can average things in cat0 spaces. That's all I'm going to say. We know everything. So we're going to ignore that. If n equals 1, we also know everything. Well, we know everything, yeah. If n equals 1, we know, turns out, mg1s is an S-1 torus modulo a Z mod 2 action. So it's a Kummer variety. And I'm not going to say anything more about that, but we know everything about it. We know completely what its topology is, what it looks like, even its algebraic structure, if you want to think.
Remember that all these graphs are just a circle with a lot of trees.
Yes, exactly. And I should say this is homotopy equivalent. Turns out you can shrink the trees. So you just have a circle with a bunch of lines coming out. And where does the torus come from? These lines, you can vary the lengths of these edges. So these lines go around circles. I'm not going to talk about that, right? If n is equal to, well, n equals 2, I showed you what the space looks like, and we know a lot about it, but things get interesting. So what about the homology of the space? Let's just start. Let's not put any leaves on for the moment. If I take trivial rational coefficients, well, this space is contractible. Let me just say this. MG20 is contractible. So it doesn't have any interesting homology, for instance. But remember this, if you pass to a subgroup of finite index, and you look at the quotient of the space of outer space modulo this subgroup of finite index, that does have homology, as long as gamma doesn't have any torsion. So a contractible space, you know, the Euler characteristic isn't very interesting, for instance. The Euler characteristic of MG20, that's the same as the Euler characteristic, yeah, is, well, it's just got, it's 1 for the Q in dimension 0. But this does have homology, and Serre noticed that if you have a torsion-free subgroup of finite index, you can define the Euler it's called the rational Euler characteristic of out of Fn of F2 to be the Euler characteristic of this finite subgroup divided by the index of the subgroup. Why is that good? Because this is independent of gamma. So if out of F2, if it's got torsion, and so there's many reasons why you can't define the Euler characteristic. It has homology in all dimensions. So you can't define the Euler characteristic as the alternating sum of the dimensions of the homology. But if you pass to a subgroup of finite index, then there is homology. You can define this other type, this variation on the Euler characteristic, and it doesn't depend on the subgroup of finite index, so it's a perfectly good group invariant. And if you compute it for out of F2, you get -1/24. So there's some homology there in subgroups of finite index. You always get something. Yeah, I guess I have to justify that a little more, but there is some homology there. So things get more interesting, even though that the space doesn't have any homology. It's kind of a boring contractible space. It's got this finite cover that's got some interesting things happening. So the question is, do these spaces have interesting topology as n gets bigger? And for small n, you can calculate the homology of all of these a and s. But let's just stick to out of fn. And for small n means n less than or equal to 7. And n equals 7 was just done last December by Bartholdi. Last December, a year ago. And you get interesting stuff. Interesting classes, excuse me, 4. H4 of out of F4, H8 of out of F6, and H11 of out of F7. There's another one in out of F7. I can't remember the dimension. Okay, so there is some homology, there's some interesting topology going on, but it's very hard.
What do you mean interesting?
Yeah, well, non-trivial for one thing. That makes it more interesting than trivial. It turns out that...
You mean these are the first non-trivial cohomologies?
Yes, these are the only non-trivial cohomologies with trivial rational coefficients up to dimension 7. This one is extremely interesting. That's another story though. But let me tell you anyway. So I told you that this group out of Fn is kind of related to mapping class groups and to general linear groups, GLNZ, arithmetic groups. For all of those groups, there is no rational homology in the virtual cohomological dimension. In the top dimension, it could possibly have homology. There just isn't any. This is the top dimension for out of F7. So this computer calculation, which I forget how many multi-gigabytes took, came up with a class. Nobody believed it because it wasn't supposed to exist. So that's interesting. Two other groups. This was done by Bartholdi, Morita, and Suzuki and Sakasai also did a computation a different way. And Jim Conant did the computation a different way, and they all came up with the same answer. So 3 times we believe it, but it's not supposed to exist. So yeah, there's interesting homology. But let me just say, what about as n goes to infinity? Things get wild. In particular, there's lots of homology. Well, let's just think about the rational Euler characteristic. So grows is always negative, non-zero, in fact negative, and it grows. The absolute value of this grows like gamma of n plus a half n plus 1/2 over n log squared n. Okay. This is was proved in November.
You mean grows in n?
Yeah. Okay. So this is what I was going to talk about today, is this Euler characteristic. This is a very new result of Michael Berinsky. Who is a physicist. And he was studying Feynman graphs. So Feynman, people who do perturbative quantum field theory, as I said, they want to understand this space of graphs. They want to do integrals on this space of graphs. One thing they have to know is how big it is. How many integrals are they going to have to do? They also would like to know how they're related to one another, but they like to count graphs. And it turns out that, so I met this guy at a conference on Feynman integrals last summer. He was good at counting graphs, and he figured this out. So let me tell you a little bit more of the story, a very little bit more of the story. Yeah, so the other thing that came out of what he did is that this number, chi of out of Fn, is closely related to zeta functions, zeta of n. Actually, zeta minus n over n. And that was a surprise as well. It wasn't a complete, utter surprise because in the 1990s, Harrer and Zagier proved that the rational Euler characteristic of the mapping class group of genus G with one puncture is, I'm going to get this wrong, I think it's zeta of 2G, maybe. Anyway, it's very closely related to that. There might be an over 2G. Yeah, I don't know. So this was a big result that a lot of people are interested in, and the fact that the outer automorphism group, so also of course rational Euler characteristics of arithmetic groups are related to zeta functions. That's old work of Harder. And so now we have another analogy between out of Fn and arithmetic groups and mapping class groups. So in the remaining 6 minutes, I want to tell you something about where this comes from. Oops.
When you say it is closely related to beta of minus n upon n,
yeah,
it is exactly equal
No.
to, or it is approximately?
It's not even approximately equal to. Okay, I'll tell you the words.
It's not equal to, like in the
No.
Jagier case, it is equal to.
That's right.
Or Harder's case, it is equal to.
That's right.
It's not same flavor.
No, it's not equal to. There's a Hopf algebra of graphs, and the Euler characteristic gives you, there's another closely related function, which is a convolutive inverse in this Hopf algebra, and that one gives you zeta of n over n. So you have to do a convolution in the Hopf algebra to get zeta of n over n. I don't, yeah, anyway. I may as well say it because I'm not going to get to it, right? And then I get to say it. This is great. Right. Now in the remaining 5 minutes, I'm going to tell you something about, in order to understand any of this, you need to understand how you do any of these computations, how you compute the Euler characteristic, etc. I told you if you want to compute something about the homology of this space, you should, of this group out of Fn, you should look at the homology of this space. So I need to tell you a little bit more about the homology of this, about what this space looks like. And I'm going to do this by saying the space of marked metric graphs has a deformation retract Kn, which is a simplicial complex. Actually, it's a cube complex. The simplices arrange themselves into cubes. And I can actually use this space just as well as all of outer space to study my group because it's still contractible. And actually, it's an equivariant deformation retract. It's still invariant under the group. So all I have to do is tell you what a cube in Kn is a pair consisting of a graph and a forest. And this is up to isomorphism. So for instance, there's a graph, and I need a forest. My forest is only going to have one tree, because I don't have much time. Whoops, doesn't show up. It needs an autumn forest. So that's my forest, and that's my graph. And how do I make a cube out of this? Well, it's going to be a two-dimensional cube because I've got two edges in my forest. At one corner, it's going to have my graph. The center, the whole cube corresponds to the graph and the forest. And how do I get the other corners of the cube? I collapse the edges of the forest one at a time. So if I collapse this one, I get there. So I did that by taking this forest and collapsing this one. And if I collapse the bottom one, I get here. So I did that by taking this graph and collapsing the bottom edge. And if I collapse both edges at once, I get here. And so there's a cube. The zero-dimensional cubes don't have any forests in them. The one-dimensional cubes have a one-edge forest in them. The two-dimensional cubes have a two-edge forest in them, etc. And these cubes are marked. Okay, so that's my space. And then a theorem of Ken-Brown says that if I just want to calculate the Euler characteristic of the quotient, the rational Euler characteristic actually of the group, I just have to add up over all these cubes, well, orbits of them, the state minus 1, the number of edges of the forest, divided by the order of the stabilizer of G phi. So in 1987, John Smiley and I proved that this is the same thing as the sum over graphs G up to isomorphism of a function tau of G over a group of automorphisms of the graph, where tau of g is the sum minus 1 to the number of sum over all forests in G minus 1 to the E of F. So this is just a little combinatorial argument to go from here to here. But this means you can actually compute the rational Euler characteristic fairly easily. And if you give me another minute, I'll do it for n equals 2. Can I have another minute?
Yes.
So for n equals 2, we know what the graphs are. There's that one, and there's that one. What's tau of this one? Yeah. How many forests are there in this guy? There aren't any. So this is including the empty set. So tau is 1. And this one, there's the 1 zero-edge forest and 3 one-edge forests. So tau is minus 2. And this one, there's 2 one-edge forests. There's a zero-edge forest, a one-edge forest, and I get 0. That's what tau is, a group of automorphisms. Well, there's 8. There's 12. And this I don't care about because tau isn't going to show up. So I have 1 8 minus 2 twelfths is minus 1 24th. Okay, so it worked. It does work. Moral of the story is, what did Berinsky do? Well, John and I worked this and managed to compute this Euler characteristic up to n equals 10. And then Zagier kind of massaged what we did and managed to calculate it up to 100. But we couldn't prove very many things about how it behaved in the extreme, and that's what Berinsky did. He managed to find out what happens as n grows. And it comes down basically to counting graphs and forests. And yeah, physicists are good at that. Turns out that counting forests is related to something called the Lambert W function. And that comes into this too, into the counting formula. And I think I'm out of time though, so I think I'll just stop.
Are there any questions?
Maybe I will ask.
Yeah.
The topic of today's talk was about graphs.
Yes.
There is something simpler than a graph which some of us like, which is a simplicial complex.
It's simpler than a graph? A simplicial complex?
No, one-dimensional.
Oh, one-dimensional, a simplicial graph.
Yeah, simplicial graph.
Are
they of any use?
I
mean, they look much simpler. Graphs are too complicated.
Yeah, but graphs are what you really need.
No, on a simplicial, one-dimensional simplicial graph, you can, of course, put length and so on.
You can make a space of simplicial graphs, yeah.
But they don't could give you anything?
Well, so what made this space useful was the fact that the space of marked graphs was contractible. So you can relate it to this group out of Fn, right? So it's true that you have a space and you have an action of out of Fn, just like if you mark your graphs, but you need a contractible space. And I'm pretty sure that wouldn't be a contractible space. So for instance, for n equals 2, there aren't any. Right? If you insist that the valence is at least 3, then there aren't any simplicial graphs with fundamental group F2. And you don't want to allow bivalent vertices, because if you do, then you can have arbitrarily many edges, which gives you arbitrarily many parameters, so your space becomes infinite dimensional. So I think, yeah, it may be an interesting space. I don't know anything about it. I never thought about it. But you could certainly make a space. It wouldn't have the same connection to, well, group theory or to Feynman integrals or things like that, because it doesn't have, yeah, you need loops.
I also wanted to ask about the new group that you introduced, A and K.
Mm-hmm.
So all the groups that appeared were very classical, like mapping class groups, GL and Z,
yeah, but you
automorphisms, and then there were those
but you already
K when you allowed base points and leaves.
But you already know these. You know about mapping class groups of surfaces with punctures.
Yes.
So the K is just the number of, is the analog of the number of punctures.
But it's not exactly that group, or it's exactly that
No,
group?
no, it's not exactly that group. It's the analog for graphs.
But it's not isomorphic to some well-known group.
Well, I think it's a well-known group, but so it's just like the mapping class group. There's a forget the punctures map, so called a Berman exact sequence. Mm-hmm. So you have ANS to ANS minus 1 with kernel the fundamental group of the surface.
Yes.
So there's a Berman exact sequence for these groups too.
Okay.
So you can see ANK as an extension of out of Fn by a free group to some power.
Okay, I see. Mm-hmm.
So yeah, in that sense. And that's very useful when you're trying to calculate Euler characteristics, because one of the other great things about this rational Euler characteristic, other than the fact that it doesn't depend on the subgroup of finite index, is it behaves well under short exact sequences. So you can calculate the Euler characteristic of the ANKs if you know the Euler characteristic of out of Fn. And that plays a critical role in what Berinsky did, although he didn't know that. So he did it all by hand, but you can get it much quicker using that fact, using a little group theory. Yeah. Yeah?
As a relation between this functional characteristic of the spaces for different n.
I'm sorry, I didn't.
Is there a relation which informal any relation for the topological characteristic of the spaces for different n?
Yes. That's a different story. So I've been talking about this deformation retract Kn, but actually the space also has spaces in infinity. And these spaces are copies of spaces for smaller ends and more leaves, in fact. So there's a nice picture there, yeah.
More questions? Yes?
I think some of these spaces should have some interest in metric models itself, because, no?
What do you mean metric models?
You was talking about this palpation of hyperbolic plane and so on and so on. Metric model, I mean something global, because all this has a flavor of something related to toric geometry and maybe because some models, no? So.
Sorry, I'm not.
Okay.
I'm not understanding.
Okay. That's me.
Okay, sorry.
Okay, let's thank Karen again.